Chapter 11, Statistics. Section 1 is gathering and organizing data. Data are measurements or observations that are gathered for an event under study. Statistics is the branch of mathematics that involves collecting, organizing, summarizing, and presenting data and drawing general conclusions from the data. Populations and samples. When statistical studies are performed, we usually begin by identifying the population for the study. A population consists of all subjects under study. Now, usually it's not realistic to gather data from every single member of the population. For example, if you're doing a study about Riverside County and people's opinion about traffic, it would be almost impossible to get a response from every single person living in Riverside County. Instead, what statisticians do is they use a sample of the population to gather their data. So a sample is a representative subgroup or subset of the population. Some sampling methods we're going to talk about are, first, the random sample, second, systematic sample, third, stratified sample, and fourth, the cluster sample. Now, in order to obtain a random sample, each subject of the population must have an equal chance of being selected. For example, let's say there are 200 employees at a particular company. If we put the names of all 200 employees in a hat and then mix them up and randomly pull out 15 names, this would be a random sample because each employee of the company had an equal chance of being selected. A systematic sample is taken by numbering each member of the population and then selecting every kth member, where k is a natural number. When using systematic sampling, it is important that the starting number is selected at random. An example of a systematic sample could be asking every 8th person walking into a store what they are planning on purchasing. When a population is divided into groups where the members of each group have similar characteristics and members from each group are chosen at random, the result is called a stratified sample. For example, dividing students into their class ranks, so freshman, sophomore, junior, senior, and then randomly selecting 10 people from each group and asking them a question about the school. When an existing group of subjects that represents the population is used for a sample, it is called a cluster sample. For example, an inspector may inspect every computer from one shipment that came from a particular warehouse to look for defects. This shipment can be used to make assumptions about the number of defective computers to expect from other shipments from the same warehouse. Statistics. There are two main branches of statistics: descriptive and inferential. Statistical techniques used to describe data are called descriptive statistics. This is based on collecting, organizing, and reporting data without using the data to draw any wide-ranging conclusions. For example, you could collect a lot of data and figure out that the average number of students in a math class at RCC is 32.5 people. This is clearly descriptive and it describes the average size classroom at RCC for math. Now, statistical techniques used to make inferences, or you can think like educated guesses, are called inferential statistics. This is based on studying characteristics of a sample within a larger population and using them to draw conclusions about the entire population. Or in other words, making like an educated guess, making inferences. For example, a study shows the median home price in Riverside County should rise in the next year. This is not descriptive, it's not for sure based just off numbers, but the stats that were calculated implied that perhaps home prices are going to rise in the future. Frequency distribution. The data collected for a statistical study are called raw data. In order to describe situations and draw conclusions, we need to organize the data in a meaningful way. Two methods that we will use are frequency distributions and stem and leaf plots. The first type of frequency distribution that we will investigate is called the categorical frequency distribution. This is used when the data are categorical rather than numerical. Let's look at an example using categorical data. Exercise 1. Constructing a frequency distribution. 25 people were asked if they prefer to watch TV, watch movies, or watch live theater. The data follow. Construct a frequency distribution for the data. So all you need to do is you need to tally up the number of responses for each category. So as I look through the chart, I see TV, TV, movies, live theater, TV, movies, movies, TV, movies, TV, live theater, TV, movies, TV, TV, movies, live theater, TV, TV, movies, 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 live theater, TV. Once you have all of your tallies, then you can calculate the frequency by just counting up your tallies. So it seems that 11 of the 25 people prefer to watch television, 9 of the 25 people prefer to watch movies, and 5 of the 25 people prefer to watch live theater. One thing you could do is make sure that you didn't miss any. So if I add these all up, 11 plus 9 plus 5, that does equal 25. So I'm pretty sure that I didn't miss any of them. And why this is helpful is if you were just given a big table like this and asked a bunch of questions, it would be very difficult to have to constantly count or compute percentages or whatever it is that you're trying to figure out. Versus this table, it's already been counted for you, so when you need to reference the data, you can just directly jump to the number rather than just a bunch of random responses. So it's just a really nice way to organize all of the data you've collected. Another type of frequency distribution that can be constructed uses numerical data, and it's called a grouped frequency distribution. So again, this one uses numerical data, unlike the last one that used categorical. So some sort of a characteristic, like what kind of entertainment do you like to watch? Or maybe it's something about like hair color. Those would be categorical. Numerical means we're using numbers, and this perchance could have like a range of numbers. So for example, if you gathered data on the weights of people in your class, there's a decent chance that no two people have the exact same weight. It would be reasonable to group people's weights into weight ranges, like 100 to 119 pounds, 120 to 139 pounds, and so on. So in our grouped frequency distributions, the numerical data are divided into classes. Here are some guidelines you want to follow when making the grouped frequency distribution. Try to keep the number of classes between 5 and 15. If you have too few classes, you probably can't gather very meaningful information from them because you have too many things in too wide of a class. But if you have too many classes, perhaps you have like only one data value in a bunch of your classes, so you aren't exactly really grouping them together. It almost might still look like a big table of numbers. So you want to keep them within this range between 5 and 15 so you don't have too few or too many. You also do not want the classes to overlap. So looking back at the example with weight, notice we went from 100 to 119 and then from 120 to 139. So there's no overlap with people who weigh 119 to 120. Like you're either in the 119 category or you're in the 120 category. We do not want to leave out any numbers between the lowest and highest, even if nothing falls in that particular class. Again, if we were doing weights, if we had a student who weighed 105 pounds and a few other students that weighed maybe 115 or 120, and then the next student weighed 185, even though we didn't have anyone between 120 and 185, we still need those classes, even though they would be empty. The fourth thing is you need to make sure the range of numbers included in a class is the same for each of them. You want the same number of weights in your first class as you have in your second class, and so on. And the last thing, the beginning and ending values have to be chosen based on how the data values are rounded. So let's look at exercise 2. These data represent the high record temperatures for each of the 50 states in degrees Fahrenheit. Construct a grouped frequency distribution for the data. All right, so there are 50 numbers here representing the highest temperature from each of the 50 states. We have 5 things we need to do to construct our grouped frequency distribution. So the first thing we're going to do is subtract the lowest value from the highest value. So take a second and pause the video and locate the lowest and highest value and subtract them. And you should have gotten 34. So our temperatures range over 34 degrees from 100 up to 134. And actually, if you want to know, this temperature of 134 degrees was recorded in Death Valley, California. So not too far away from here. All right, so now we have the range that our values are going to span, so within 34 degrees. What we want to figure out is how many classes should we create for our grouped frequency distribution. And this is kind of up to you. They have to be between 5 and 15. You want to pick something that's useful though, right? You don't want to have a bunch of classes that only have one data value in it. And you also don't want to have too few classes so you have like 25 of the 50 data values in one class. Maybe we want to span like 5 degrees per class. So what we could do is we could take our range, which is 34, and we could divide it by 5. If you do that in your calculator, you get 6.8. So I'm going to say this is roughly 7. So if I make classes that each have 5 temperatures in them, I'm going to need to have 7 classes. Now this is not the only choice. You could say maybe that you want 4 different temperatures in each of your classes, like 100, 101, 102, 103, and that would be one class because that's 4 temperatures. So you would divide 34 by 4. If you did that, you get 8.5, so you would need about 9 classes. So it's really up to you, but for now, I'm going to pick the first one we did, and I'm going to choose to have 7 classes. Step 3, we want to start with the lowest value and add 5 to get the lower class limits. So the lowest value we had in our chart was 100. And if I add 5 to that, my next lower class limit will be 105. If I add 5, I'll be at 110. Notice so far I've come up with 3 lower class limits. So this is class 1, class 2, class 3, and I want 7 of them. So I'm going to have class 4, class 5, class 6, and class 7. If I add 5 to 110, I'll go 115, 120, 125, 130. Now, my classes are not allowed to overlap. Let's just do one of them here, but each of my classes should have 5 temperatures in it. So my first class will have 100, 101, 102, 103, and 104, right? Notice that's 1, 2, 3, 4, 5 temperatures. So I'm going to go up to 104. And this is good because if I end at 104, it makes sense that my next class would start at 105. So if I'm going to do 4 more temperatures, I'm going to end up at 109. So that's 105, 106, 107, 108, 109, which is 5 temperatures. Then my next class would start at 110, and I would continue, which is actually what we have for step 4. So set up the classes to find the upper limits. So just take a second to fill out all of the classes that we were writing before. And we should be left with these classes. Notice each of them have 5 temperatures within them, and they do not overlap. We have between 5 and 15 classes. We're doing good. Now we want to tally. So I'm going to ask you to pause the video. You might even have to rewind if you're doing your notes on paper rather than having it printed, and go look at the data, and you're going to tally how many of these temperatures fall into each class. So for example, I'll start with you. In the top range, I have 112. I'll do the first column, 112, 100, 107. Let's look at those. So this would be 112, this would be 100, this would be 107. And if I finish that column, I had a 122 and a 120. So go through and tally for every column through the 50 pieces of data, and then come back and check your work. And you should end up with this. Now what we're doing here is actually step 5, which is to tally your data and record the frequencies. So hopefully your tallies match mine. The frequencies I have are 3, here I have 8, in this row I have 16, 13, 7, 2, and 1. And again, it might be helpful to add these up to make sure you didn't miss any. We want to make sure that we add up to 50. So that's 10, 18, 21, 34, 40, 50. So we did add up to 50. And again, this is just another way to kind of condense all of your raw data down into some useful information that you can quickly grab numbers and, talk about things you noticed, get some inferences from this data, or even some descriptive statistics. You might be able to calculate like an average weight, or you can say which class contains the most temperatures, etc. All right, and lastly, we have the stem and leaf plot. So another way to organize your data is to use this thing called a stem and leaf plot. Sometimes we call it a stem plot. Each data value or number is separated into 2 parts. The very last digit is what we call the leaf, And what comes before that digit is what we call the stem. For example, if I have a 2-digit number like 53, the last digit, the 3, is my leaf, and what came before the 3, or the 5, is my stem. Similarly for 72. If I have a 3-digit number like 138, the very last digit, which is the 8, is my leaf, and what came before the leaf, or the 13, would be my stem. Same thing if you have decimals. So if something is rounded to the 10th place, so your stems and leaves are based off the tenths, then you would let the 4, or what's in your 10th place, be your leaf, and the number in front of that decimal point would be your stem. So in exercise 3, we have some data about unemployment rates in 2015 for each state, and we want to draw a stem and leaf plot illustrating the data. Well, these are all done with a decimal point, and we really only have 2 digits here. We have the 10th place and the ones place. So we're going to pick our leaves to be the 10th place, which means that our stems are just going to be the values in the ones place. So what we need to do is we need to determine our lowest value in this data and our largest, so lowest and highest. So the smallest one that I see is 2.8, and the highest data value that I see is 7.6. So this means that our stems need to range from 2 to 7, and we can't skip any numbers. Even if you don't have any leaves for these stems, you still need to write out the numbers. And then how you write out your leaves is you go from least to greatest, and you write them next to the stem. So for example, I see 2 numbers that start with a 2. One of them is the one I just had, which is the 2.8, and the other one is a 2.9. You need to write the leaves from smallest to largest. So the smallest of those would be 8, and then the next one would be 9. So if I was reading this stem and leaf plot, knowing that the leaves are for my 10th place, I would know in my data that I have a 2.8 and a 2.9. Let's do this for the 3s. So let's go through and let's circle all of the values that start with a 3. So I have a 3.7, 3.5, 3.6, 3.7, 3.7, 3.6. I think that's it. So the smallest of all of these leaves would be the 0.5. And then I have 2.6s, so 6, 6. And then I have 3.7s. And it's also important when you're writing out your leaves that you line them up with the number that was above them, because if you're very organized, it can give you a good idea about what your data would look like if it was graphed. So I want you to try to continue this on your own and go through and write out all of the leaves for each of these stems, again from smallest to largest, trying to make sure your numbers line up in the columns. So pause the video and then come back and check your work. And you should be left with this. So what we noticed is that the majority of our numbers fall within the 4s and 5s, 5 containing the most, and the least of our numbers fall within the 7s, right? One thing you could do, and the reason I made you line these numbers up in the columns, is if you take your paper and you turn it. I can't exactly turn my screen, or at least I don't know how. But if you turn your paper this way, you'll see kind of that these look like columns, like in a bar graph. Like you have one with 2, the one next to it has 6, and you have 15, so it's like way higher, 16, 10, and then 1, right? And if you look at it this way, which is your stem and leaf plot flipped over, it kind of gives you an idea of the distribution of your graph, or the shape of your graph. Like if you were to draw a line over it, you can kind of see how your data falls. And we'll get more into this later in the chapter, but it is really helpful in trying to understand certain aspects of your data if you get an idea of the shape of your graph. So I think that's a really cool thing that you can grab from a stem and leaf plot, which is just where you're writing out numbers, as long as you just write out in a pretty organized fashion.